Welcome back, everybody. We're going to continue. This is, of course, Math 65. What are we on? Lecture day 3 of content. First day was just introductions. This is continuing 1.5. It's like 1.5b. So we talked about continuous functions on Tuesday. And I even had said near the end that we can define a continuous function as one that's continuous every point on its domain. That on its domain is a kicker. So f of x equals 1 over x is continuous, is a continuous function because x equals 0 is not in its domain. So this one is continuous. If we shift over to f of x equals 1 over x for x not equal to 0, and say 1 if x equals 0, then this one is not continuous because x is now, or the function is now defined at x equals 0, and it's not continuous there. So that one would not be continuous, but the first one is. It's a little nitpicky, and I don't know that you're ever going to really care about it, like describing whether something's continuous or not. When you start getting to the point where like having the name continuous function matters to you, most of this shit's going to be second nature. So there's that. So then we can go on to our functions, our theorem on continuous functions. If a function is continuous at a point, if we have like functions f and g, and like let's say f of x is x squared plus 1, and g of x is e to the x. We can say that those are both continuous functions everywhere. There's no holes in the graph. There's no breaks in the graph. So if we add the functions f of x plus g of x, the outcome that function together, f plus g is e to the x plus x squared plus 1. It's also continuous everywhere. And so we can go through all the little options. Adding them is the same, subtracting them still has it, as long as they're continuous. We did a lot of these things. If you look at it, it's like a real number, like the properties of real numbers you learned a long time ago. This is how real numbers work. If two numbers are real numbers, you add them together, the outcome's a real number. Same thing with continuity. Continuity works much the same way. If we have two continuous functions, the product of them is continuous. We can multiply by a scalar k. A scalar means a constant value. We can do quick f divided by g, and it will be continuous everywhere. And I chose a g of x that does not have a value where it equals 0. So e to the x does not equal 0 anywhere. We can raise them to exponents. So any power of f is still any integer power of f is still a continuous function. We can take roots of it, and so long as the root doesn't create a negative spot, we're good to go. So, with those all in play, I know I got to give you guys some time to write. We're going to look at an example and use those rules to figure out one of the outcomes. Give everyone another minute to write. All right. So we're going to say F and G are continuous, and the value of F at 5 is 7. We want to find G of 5. We have the limit as x approaches 5 of 2 times f of x minus g of x equals 11. So we are going to use those limit rules up above. Here we have 2 different functions being subtracted. And so like this says them together is 1. That means individually they work 2. We could separate this out. I could make this limit as x approaches 5 of 2 times f of x minus the limit as x approaches 5 of g of x equals 11. This is utilizing that differences property up above, f minus g. And we showed if there's a constant times a function, we can move the constant to the outside. Which is good because now, since it's continuous there, this is just f of 5, which is it as 7. So this first part is 2 times 7 minus the limit as x approaches 5 of g of x equals 11. So that's 14. So we can subtract 14 from both sides. And I have negative limit as x approaches 5 of g of x equals 11 minus 14 is negative 3. And now we can just divide by negative 1. The limit as x approaches 5 of g of x is 3. Yeah.
Oh, wait, never mind. I was gonna ask how subtracting 14 made the limit a negative.
It was already a negative.
Subtraction.
Yeah, it was a subtraction. Good question. Too much carbonation. I don't want energy drinks in the morning anymore. It's not any fun. And I don't think I feel as alert as if I just had coffee. That's weird. Right, I'm apparently not an energy drink doer. I've had Bang, the cotton candy. I like that cotton candy Bang. It's pretty tasty. Does anyone need this out longer? All right, let's proceed. We're going to have a theorem. If G is continuous at A and F is continuous at G of A, we can do the composite F of G. It's continuous at A. So as a reminder, F O G means F of G of A. Give you a second to write that down and we'll go through and think it through, make sure it makes sense. You should put X here. That's an X, not an A. Because we're going to lead to that. So the G is continuous at A means the limit as X approaches A of G of X equals G of A. And this part says F is continuous at G of A, says the limit as X approaches G of A of F of X equals F of G of A. So we're doing two different little limit things here. So we have the limit as X approaches 16 on the example. The limit as X approaches 16 of the natural log of, on the numerator, we have square root of X and then minus 2. And in the denominator, we have 6 minus the square root of X. This is kind of like saying the outer function is the natural log of X. And the inner function is that square root of X minus 2 over 6 minus square root of X. Does that make sense? Does that track? If I stick this in that, that makes this the limit as X approaches 16 of F of G of X. The way I have it right now. It's probably been a while since you've dealt with composite functions. So we should do these two limits separately. What does the limit? Let's do the G of X one first because it's on the inside. What does the limit as X approaches 16 of square root of X minus 2 over 6 minus square root of X equal? Is it continuous at that point? Does it exist there? Is there any problem plugging in 16 into that function? No, it doesn't create a problem. So let's just do that. We get G of 16 And that is square root of 16 minus 2 over 6 minus square root of 16. So we have 4 minus 2 over 6 minus 4. 2 over 2 is 1. And you'll actually see at this point, the hard part of the limits goes away. Because if we follow that along, what we're doing is showing the limit as x approaches 16, really of f of x, but it was natural log of g of x. And g of x at 16 was 1. So we have the natural log of 1. That might be easier to show as natural log of g of 16 first. And that goes to natural log of 1, if that helps make it clear. And what is the natural log of 1? 0. That's one of those you should know without a calculator. Probably the only natural log you should know without a calculator. Or, no, that's not true. You should know natural log of e without a calculator as well. So the whole limit was 0. Are you guys okay with that? All right. So to go ahead and write down the intermediate value theorem, then work together, we're going to write a picture. The intermediate value theorem says if f is a continuous function on a closed interval from a to b, and if y sub 0 is any value between f of a and f of b, that should say then there exists a value c that's between a and b such that y of 0 equals f of c. That's a lot of words, but when we see the graph, this is gonna you're gonna be like, that totally makes sense. Seems like a no-brainer. If anyone remembers from algebra finding the roots of a polynomial, like that p over q shit, p over q, like one of the processes of doing that kind of stems from the intermediate value theorem. We'll do the proof in a second. I'll probably do the proof on another page. I want to draw a picture that everyone can see. So make sure everyone's on the same page with intermediate value theorem. let's say that's f of x. That is f of b. That is f of a. So far, I just grabbed just some random function, picked an A and B that I didn't even identify. It could be 1 and 6. Who knows what it is? It doesn't really matter. The point is that if I have the function and I have two x values, I can find the two corresponding y values that go with it. This meets the whole f is a continuous function on a closed interval a to b. Now let's take a look at the y naught. If y naught is any value between f of a and f of b. So y naught is, let's say y naught is right there. That's between f of a and f of b. Well, if I come over here, I can find a point on the graph where this has got, there's a value c that's between a and b. So it says then there exists a value c between a and b. I just drew where it was, such that y0 equals f of c. So by picking c to be that point right there, y0 is now f of c. And that green line, that green section can shift. I just drew one that was in the middle, so it's easy to see. But you can see no matter which y we pick over here, between f of a and f of b, we could draw a line, a little dotted line over to the function, and it's going to intersect it somewhere. And if we go downward, we can find the corresponding x value that goes with it. Does that make sense? Anybody have any questions? Because it's kind of like important to the idea of the intermediate value theorem. If you don't understand what's going on, like the next thing isn't going to make a lot of sense. All right. So then we have, the question is, and I'll write on another piece of paper. I'll leave it up there for a second. We have proved that the function I'm almost off the screen. Proved that the function f of x that equals x cubed now I am off the screen. Let me write it down here. F of x equals x cubed minus 4x squared plus 5x minus 3 has a root. What's a root? Anybody got that? Remember this? This is algebra.
Is it where the graph hits the x-axis?
Yes. A root is where the graph hits the x-axis. Where f of x intersects x-axis. What's special about the entire x-axis? Y equals 0 there. So. Let's draw a little mini sketch of our little intermediate value theorem graph right here. And I'm just going to focus on the f of c part. So f of c is going to be 0. And we're trying to find c. So this is our x-axis. That's our x-axis. This is y. And we're trying to find the value c so that our function, it could do something like this, or it could be downward. Or it could just kiss the graph and bounce off. It could do one of those. I tried to use 3 different colors. I don't know if they show up very well, especially if you're in the back or on Zoom. But like the red one crosses left to right, going upward. The green one's going downward. And the blue one's just going upwards, hitting the y-axis and bouncing back down. How can we use this idea to try to figure out where the roots are? Using this intermediate value theorem idea we have up here. This means we have to have an f of a down here and an f of b up here. What's special about those? One's positive and one's negative. This only works when the x-axis is what you're looking for. F of b is greater than 0 for any of the f of b's. No matter which line, where I put that line above the x-axis, they are all positive. And f of a is less than 0 everywhere below the x-axis. So what we got to do to show there's a root, what do I need to do to show there's a root? We should any idea how I can utilize these properties of f and a and f of b we just talked about? Well, let me redraw that without all the extra shit on there. Let's just draw the red one real quick. This might help. What do I got to show? Matthew.
Just show that across the x-axis.
But how?
You have to show this two y values that have 0 between them.
That's what we're going for. But how can I show that? How can I show that there's 2 y values so that 0 is between them?
One's negative, one's positive.
There we go. That's what we want. We should show that for f of a, for x equals a and x equals b, specific x's or specific a's and b's. This is a dead green pen. I need to get rid of it. For specific a's and b's, f of a, comma, f of b, one is positive, one is negative. You'll gain, I will pause every once in a while and try to force an answer out of you guys, because you guys will gain more from this class if you reason it out rather than me just trying to pump your head full of knowledge. So. There's no real good approach to do this. I would recommend starting with one of the easiest numbers to do this with. What is one of the easiest numbers to evaluate f of x at? 1 is really easy. It's not the easiest, but we'll do it. F of 1 is pretty easy because all of the exponents have no effect. 1 to any power is just 1. So that is probably the second easiest number to check. I've got 1 minus 4 plus 5 minus 3. 5 minus 3, or 1 minus 4 is negative 3. 5 minus 3 is positive 2. This looks like it's adding up to negative 1. So pictorially, and I don't know if it's going red up or down, left or right. I'm not sure. I know at 1, f of 1 is down here. It's at negative 1. What's another easy? Oh, I'm off the screen. What's another easy number to check? 0. 0 is the easiest. F of 0 kills every exponent or every variable. Every variable in the x cubed. Let me rewrite this over here. F of x equals x cubed minus 4x squared plus 5x minus 3. F of 0 destroys all the variables, and I'm just left with negative 3. Which means that's over here. So it looks like it's going upwards like this. Maybe I should pick values higher than it. What's the next number you guys want to try?
4.
4. Let's do 4. Because you wanted Hefe to cube 4. No problem. We'll plug it in. 4 cubed minus 4. Actually, 4 is a good choice. Because this is both 4 cubes, so that goes to 0. So f of 4 is 20 minus 3 is 17. So we have one that's positive, one that's negative. There exists an x. There exists. I don't know if you've ever seen this notation. They do a backwards capital E. That means there exists. That's some fun math jargon for you. The other one that they use that's got capital letters is for all. And they use an upside down A. That looks funny. There exists is right though. Pretty sure 4 all is 2. So there exists an X in between 1 and 4 such that f of x equals 0. And we'll say that's C. I don't know what the value is of C is, but there exists one. Any questions? You guys ready for the next question? Nope, I see some pins still going. Hefe's rushing. So if I were a sadistic buck, what would I make the next problem be? Find the root. We're not gonna deal with that one. We're gonna deal with another one. Find the irrational root of f of x equals x cubed plus 3x minus 2. Let's just say to 1 decimal place. And I want you guys to work on this in here. Work together if you'd like. In fact, I encourage you to work together. Apply what we did in the last problem to this problem and find that x value. I'm going to pause the recording for a second while you guys work on it for a little bit. Just making sure you guys do okay. If we do f of 0, we have -2. And we do f of 1, we have 1 plus 3 minus 2, positive 2. So it's got to cross somewhere. Does everyone have an answer? If not, keep going. Or look at someone that's sitting next to you that isn't doing it, ask them if they got an answer, and be inspired by their great insight. Yeah, this is gonna take a calculator. If you're doing this without a calculator, I know you ain't doing it. Just stopped. Unless you're fucking exceptional at doing decimals to exponents. And if so, bravo, you're gonna fucking be a far better mathematician than I am. And I'd like to think I know what I'm doing. Who in here has an answer? What's your answer?
That's right.
Yeah, one decimal place. 0.6. 0.6 is the answer. How did you go about doing it?
I did 0 and 1, then I did 0.5. And then I realized it would even be a little bit bigger than 0.5, so I just went 0.6.
Okay, that is a good approach. There's two main approaches to this. Once you found out it's between 0 and 1, one option is, and I am not going to do it because it's fucking calculator intensive. You start at 0, you go to 1, and you just do 0.1, 0.2, 0.3, 0.4, and all the way down, and you're down to 0.8, 0.9, and you figure out where, between which two decimals it goes from negative to positive, or positive to negative. And then you like drill shot down there. What's your name? Yeah, Cohen. So what Cohen said is, I know 0. It was I'm saying it right, Cohen.
Yeah.
All right. 0 was over here. 1 was over here, and the values for those, 0 was -2, and 1 was +2. Let me get back on the screen. He said, "Fuck it. I'm just going to cut this thing in half. Let's check 0.5. If you check 0.5, you get a -0.375. And so that told him these are both negative, it's not over here. Now I've got negative and a positive here. And this is where he started doing like a drill shotting down. Just he went up to 0.6 and did that. Another approach is just keep finding the middle point and cutting this bastard in half. If you do 0.75, 0.75 gets you 0.67. And at this point, 0.5 is, the 0 is closer to 0.375 than 0.67. Maybe give 0.6 a try. 0.6 when you do it is really close. It's 0.016. I hope that's not where you stopped. At this point, zoom in again. And 0.5, I have a negative, 0.6, I have a positive. You should try 0.55 as well. This is the middle one, and this will show you whether to round up or round down. 0.55 is negative 0.2, which means it's not in this region, it's in this region, and anything above 0.55 would round up to 0.6. So f of 0.6 is approximately 0. It's not equal to 0. As we showed here, it was 0.016, but it's pretty close. Does that make sense? Good work, Con. So you could either get down to 0.5 and 1 and then do every one. This idea is like we're squeezing this down. We got a negative and a positive. We want to just keep squeezing that shit, finding the new next negative, next positive, until like they get really close to each other. Graphically, and I did all these calculations on Desmos. just so I wouldn't have to do them again slowly on the calculator in front of you. I can see it's there, but we can eventually drill down and show that to 1 decimal place, it's closer to 0.6 than it is to 0.5. And if we really needed to know, we could technically go far enough by hand to get down to 0.5961, but that's tedious. That takes a while. You got to keep doing this squeezing or keep doing a table, like a bunch of tables. It's time consuming. Cutting in half frequently, that's a really easy way of doing it. Let's take a 5-minute break and then we'll do 1.6. So we're going to take a look in 1.6 at the continuity of trigonometric functions, and conveniently, all the trigonometric functions are continuous on their natural domain. Sine and cosine are both waves. They don't have any breaks in them. Tangent has breaks in it because tangent sine over cosine is every once in a while cosine equals 0, but we don't include those values in the function of tangent or in the domain of tangent. So tangent is considered continuous. With that in mind, we can use those rules of continuity in 1.5 to apply it to examples like this. We've got the limit as x approaches 2 of sine of x squared minus 4 over x minus 2. We can pass the limit in, and we're going to have sine of the limit as x approaches 2 of x squared minus 4 over x minus 2. If this works, then the answer will be the sine work. If the limit as x approaches 2 of that inner function doesn't have a value, then sine breaks. But other than that, this should work. So at this point, what will we do? Factor the top. Hopefully, if you've been working on your homework, this will look familiar. Factor the top. And I still have a sign outside that I didn't leave room for. And I can see this is going to be the sign of the limit as x approaches 2 of x plus 2, which should give us sine of 4, which is going to have some weird decimal value. It'll be less than 1. Oh, it'll be negative. Sine of 4 should be negative. Sine of pi is 0, and then pi is 3.14. 4 is going to be below the x-axis for this sine value. So that's just do an example of how we can do it with that. There are some things that pop up a lot or that we use later on. One of them is sine theta over theta. Another one is 1 minus cosine theta over theta. We're going to prove those two values, but we're going to start it off with something called the squeezing theorem. So the squeezing theorem is, let's say we've got g of x and f of x and h of x, and that f of x is between g of x and h of x for all h, or for all x. Now maybe I'll graph this. Let's say f of x looks like that, and h of x looks like that. I'm off the screen. And we had some g of x that goes like this. That's my g of x. It's between f of x and h of x for all x. The squeezing theorem says that if we can show that the limit of f of x, if we can show a limit of f of x as x approaches some value a equals the limit as x approaches a of h of x. And we know g of x is between it. We're like, as we go to infinity, this is happening right here. These two functions, f of x and h of x, are squeezing closer and closer and closer together. Eventually, for these two, the way I was drawing the graph, this looks like the limit is 0. And the limit is 0 on that one. So the limit of g of x will be 0 as well, because it's trapped in this funnel. And we can figure out what the outer limits are, but you may not be able to figure out the inner limits. We are going, does that make sense? Like we're squeezing it down? Yeah,
The
Matthew.
limit of g of x would also be 0.
Yes, yes. So that shows by force, limit of g of x is 0. Because it's being squeezed down. It's below a certain amount above it and above the amount below it. And those two values are getting closer and closer and closer until there's no real difference from them being the same value. And g of x is still trapped in it. So it's got to be 0 as well. This was showing one with like x goes to infinity. The example we're going to prove, and two examples we're going to prove in a second, go to x equals 0, or theta equals 0 here. I chose theta, but we could use x. You guys ready for the next part? Let's take a look at this. Does anyone need this page up longer? All right, I'm going to write this on a blank page real quick. We are going to look at the limit as theta goes to 0 of sine theta over theta. And we are going to show that it goes to 1 by using the squeeze theorem. There is no way you're going to intuit what those two theorems should be. So I'm just going to say from between 0 and pi over 2, including 0, that's important, we need the 0. Between 0 and pi over 2, we have 1/2 tangent x is greater than or equal to 1/2 x. I don't think I can include pi over 2 since I have tangent x there. Which is greater than or equal to 1/2 sine x. And you're going to be like, where the fuck is sine x over x in this? This is non-intuitive. Before I go through the proof, I'm going to show you this is true real quick on Desmos. In fact, maybe we should do a little bit wider. I don't know if it's always true. Let's see. Let's go negative pi over 2. Come on, fucker. C. Will be, there we go. This might be a little bit easier to show with negative pi over 2. Let's see that on the left. I'm gonna use negative pi over 2 on the left, just for illustration purposes, because 0 is in between it. And that's what we're looking at for theta. All right, so I'm going to show you that that inequality holds. My red graph is 1/2 tangent x between those 2 points. 1/2 sine x is like that. The green line, and 1/2 x is between them. It actually switches order right here. Maybe we should stick with 0. Yeah, we'll stick with 0. We can see it's between them the whole way. The point is this inequality holds. So what we're going to do is we're going to take this and we're going to multiply it by 2 over sine x. The motivation is behind this is we're trying to get this. We want this to look like sine x over x, but the closest we can get to it right now is x over sine x. So if I multiply by 2 over sine x, and I've got 2 over sine x here, and I've got less than or equal to 2 over sine x times 1/2 x. And I've got 2 over sine x here is less than or equal to 1/2 sine x. We can clean some stuff up. I put an equal sign there. That's not supposed to be an equal sign. It should be 8 times. Tangent x, though, is sine x over cosine x. And since we've got the 1/2, I'll put the 2 down below. So that's what I'm multiplying by on the left. Yes.
So on problems like these, will the inequality be given to us, or is that something we have to?
The ones you'll need for the homework are going to be the ones we're proving in class. And you won't need the inequality anymore. You just need to run with what you got. You'll see an example in a second.
Okay.
You're not gonna, yeah, there's no reason for you to. Some math genius fucking came up with this shit.
Okay. And one more question. What did we do to the middle term, the 1/2 x?
We're multiplying everything by 2 over sine x. The idea is we want to end up with it looking like this. We're not going to get that because x is in the numerator, but we can get x over sine x, and then we'll flip it. So that's the motivation behind what we're doing here.
Gotcha.
And so if we multiply by 2 over sine x, that inside the 2 and the 1/2 cancel out. The x is on top and sine x is on the bottom. So that part, once we get here, I've got to just flip it. So over here, I've got 2 sine, this is 2 sine x times sine x over cosine x, or sine x over 2 cosine x. So that's what I'm doing right there, this part right here. It looks like the sine x cancels out and the 2's cancel out, leaving behind a 1 on everything. We have 1 over cosine x on the left, which I did right up here. And on the right, here the sine x is the denominators, here sine x is effectively in a numerator. The sine x's cancel out and the 2 and the 1/2 cancel out, and we have that. Yeah, this is some shit. You're like, what the fuck? Where did they come up with this? This is some bullshit. You expect me to know how to do that? No. I don't expect you to come up with this shit at all. If you could come, if you were given this and you came up with this without any guidance or help or clue, you're in that Einstein, Newton fucking category. You're changing the world one day. Coming up with that inequality to get this idea. All right, so at this point, the rules of algebra and inequality says if we flip this, we flip the signs. So this will turn into cosine x over 1, which is just cosine x. And the inequalities flip as well. Sine x over x is less than 1. I've been using theta, or I said theta up there, I've been using x. We'll just keep going with x. The idea here is we now apply our limits. And what is the limit as x goes to 0 cosine x? Can we evaluate cosine x where x equals 0? It's 1. Yeah. So this is 1 over here. And this is a constant function. There is no x. So the limit doesn't affect it at all. So at some point, this is getting down to, it's between 1 and 1. So by the squeeze theorem, the limit as x approaches 0 of sine x over x is 1. Later on in chapter 2, it might be chapter 3, we will show you a much easier way to prove this, where you don't need to know some tangents and shit like that. There's no magic going on. It's called L'Hopital's rule. It's a great, it doesn't look like anything like it's spelled. It's a great little rule. And it doesn't require any of this magic. But let's face it, coming up with this shit is magic. Any questions? All right. Does anyone need this a little longer? You look like you're still writing back there. Is everyone good? All right. So we're probably not gonna have a lot of room to write this, so I'm gonna grab a fresh page. Since I write like fucking King Kong up here. Like I'm in kindergarten and the fucking letters are like an inch tall. Just so I can make it appear on the screen. What we're gonna do is the limit. As x approaches 0 of 1 minus cosine x over x, we want to prove that that equals 0. So we're not going to come up with some bullshit inequality here. We're past that. We're going to use what we had from the last term. We're going to take advantage of sine x over x. I don't have any sine x's in here, but I can get one. What we're going to do is we're going to take 1 minus cosine x. I'll apply the limit in a second. We have 1 minus cosine x over x. We are going to take advantage of sine squared theta or sine squared x plus cosine squared x equals 1. That's the Pythagorean identity for trigonometry. And so sine squared equals 1 minus cosine squared. So if I want to end up with a 1 minus cosine squared, what I need to do is multiply this by 1 plus cosine x. But if I do it on top, I have to do it on bottom. Here we're taking the advantage of the whole a minus b times a plus b equals a squared minus b squared. And I'm going to get 1 minus cosine squared x over x times 1 plus cosine x. And we still got our limit going on. Don't forget all that. I didn't leave a lot of room for it. There is no problem by multiplying by 1 plus cosine x, because as x goes to 0, this goes to 2 over 2. The fraction that I multiplied by. All right, so the next thing we're going to do is we're going to take advantage of that trig identity up there, and we're going to say the top is equal to sine squared x, and the bottom is equal to x times 1 plus cosine x. Everyone good with that? So, like the idea so far? Who would have guessed that trig would already be coming back to bite us in the ass? Right? You're like, we don't need this shit. It's chapter 1. It's already fucking here spoiling shit. You think this is bad? Wait till the example I'm going to make you guys work on together next. Before we get. All right, so I want to have that sine x over x. So what I'm going to do is I'm going to break off part of that sine squared x. And we're going to have another, that turns into sine x over sine x. We're going to turn that into 2 limits. And under the first one, we'll put the x. And under the other one, we're going to put 1 plus cosine x. And these two are multiplied together. This is taking advantage of some of those limit rules. Okay. We know this one. we just proved that as 1. What's the limit here? Can I plug in? What you should always ask, can I plug in what we're going the limit for and get a real number? If I can, you're good to go usually. There's no reason the limit should be different. So can I plug in 0 to sine x over 1 plus cosine x and get a number? Why not? That's a real number.
Is that okay though?
Yeah,
Oh, yeah, then, yeah.
yeah. This ends up being 0 over 1, which is just 0. And 1 times 0 is 0. We have just showed what we were trying to prove. The limit as x approaches 0 of sine squared x over x times 1 plus cosine x is identical to the limit as x approaches 0 of what we started with, 1 minus cosine x over x. And that equals 1 times 0, which is 0. And that's what we wanted to prove. Yeah,
So when we plug in 0 for x, for like sine and cosine, we're just multiplying the two, we're not actually like finding the value of 0.
sine of 0 is 0.
Is the sine of cosine, what is it, -1?
Cosine of 0 is 1.
So would it be 2 on the bottom?
Yeah, it is 2 on bottom, my bad. I realized as soon as I fucking said it. As soon as you asked and I started saying, oh, I fucking rushed through that. Yeah. That's. This goes to 0. That goes to 1. And I've got 0 over 1 plus 1. Good call. I bet other people were going, what the fuck do you do there? That's some magic bullshit. I don't know that that's 0 over 1. Yeah, I was wrong.
Still 0.
It's still 0, but it wasn't 1 on bottom. All right, you guys ready for me to ruin your day? Because we've got 23 minutes to do one problem, which means I'm going to make you guys work on this for a little while, and then we're going to do it together. Find that limit. Now, I'm going to give you a pro tip here. Whenever you have tangent and cotangent, you're almost always better off switching that to sines and cosines. Once you've switched to sines and cosines, you're going to have a fraction on the top and a fraction on the bottom. Fucking multi-tiered fractions or fractions in fractions suck. Get it down to a single fraction by manipulating the fractions. And you'll see what it looks like, and then you'll have a little wiggle room. You're going to have to still pull some bullshit at that point, but I hope if you look at what we did with the sine x over x, that bullshit will pop out to you. Please work together. This is not intuitive, but the struggle is going to be real. And if you struggle through it a little bit and then see how it goes, I think it's going to be better for you in the long run. So work on that for 10 minutes. I'm going to hit pause on this. So we're going to do the limit as x goes to 0, sine of 3x, cotangent 5x, x on bottom, cotangent 4x on bottom. I'm going to start off doing what I had said with writing the cotangent 4x as tangent 4x on top. This should speed it up some. All right, now I'm going to bust those down into cosines and sines. This is the limit as x goes to 0 of sine of 3x over x times tangent is sine over cosine, so cotangent is cosine over sine. And tangent is the sines on top. I'm gonna group these up. I'm gonna leave the sine of 3x with the x. And I'm gonna put the cosines together, break this into a bunch of limits here. We're gonna put the cosines together because if I go to 0 for cosine 5x and cosine 4x, that's just gonna go to 1. That's gonna go away. And we still have limit as x goes to 0 of sine of 4x on top and sine of 5x on bottom. Let me pause and give you time to write down all this insight. So we have an issue here. We know that the limit as x goes to 0 of sine of x over x equals 1. But I have 3x inside the sine and x on bottom. That's not the same thing. We can't jump to that conclusion. But what we can do is we can make the denominator look like 3x. Just focusing on this piece right here, I am going to multiply that by 3 on top and 3 on bottom. And I'm going to circle the rest of that as stuff we're going to come back to in a second. Come back to. Now, if you're comfortable dealing with the 3x, how it looks with the top and the bottom and recognizing it, you're fine. But a good idea is to go like, let's say u equals 3x. Then this looks like 3 sine u over u, which is in the right form. Right? That looks like a similar form to that, other than the 3 out front. But a constant just means we multiply the answer at the end. The question is, what happens with u? We start off with x goes to 0. If we're doing x goes to 0, what happens if we look at 3x? What does it go to? If x goes to 0, what's 3x going to? It's going to 0 also. So that means, and u is the same as 3x. So I can do this as the limit as u goes to 0 of 3 sine u over u. So we've done some replacements. We've got that. I can pull the 3 out. Is everyone okay with that operation? And we already know this part right here equals 1. We know what that is. That's 1. We still have the 3 in front. 3 times 1. So 3. That part equals 3. So at this point, I have 3 times the limit as x goes to 0 of cosine 5x over cosine 4x times the limit as x goes to 0 of sine 4x over sine 5x. Does this first limit have a value? Can I plug in 0 for both things and get an answer? Yeah. They both end up being cosine 0 on top and bottom. Even if you didn't know cosine 0 was 1, you still have the same thing on top and bottom. This entire limit is 1. So all we got to really figure out right here is this. We're down to 3 times the limit as x goes to 0 of sine of 4x over sine of 5x. Now, this is how I would recommend doing it. We're going to break that up into 2 fractions. Sine of 4x over 1 and sine of 5x on the bottom here. To pull that same bullshit we just pulled with the 3x, I need a 5x up here, which means I'm going to put a 5x down here. And over here, I need a 4x down here, which means I'm going to put a 4x up here. And I'm going to group it the way it will be more productive looking right now. I've got 3 times the limit as x goes to 0. I need the sine of 4x right there over 4x. And then that's this part right here. I still have that 4x over in the front. I'm going to put that right here. I also I want the 5x to go with the sine of 5x. I'm going to put 5x right there and sine of 5x down here. And I'll take this 5x and I'll put it right here. So it looks like I didn't need so many x's. It looks like I can cancel out these x's right here, right? Those were extra. I didn't need them. I can pull that 4/5 out and I have 3 times 4 is 12. 12 over 5. Limit as x goes to 0 of sine of 4x over 4x times the limit as x goes to 0 of 5x over sine of 5x. On this, you could do the same thing with the u. We could do u equals 4x here. Here we can do u equals 5x here. It's okay that this is upside down. If the limit as x goes to 0 of sine x over x is 1, then we can flip that over and it's still the same limit. It's also 1. So by doing the U substitution, this is gonna go to 1. This is gonna go to 1. And we're left with 12 fifths, which equals 2.4. And it's 10 o'clock. So when you're done writing, you're free to GTFO. If you've got questions, I'm here. Some complicated shit, right? The struggle is real. I have been in your shoes. This isn't easy. But as a reminder, I will be in the Mesa Center over on the Visalia campus, John Muir 115, I think, on Saturday from 9 to 12 in the morning. If you want to come in and ask questions, I will be available on the weekend. I'll send out an announcement today. Yes. Let me go through the info I need. CRN is 16440. 965. Days and times is Tuesday, Thursday, 8 to 10 a.m. David Jones. There you go. Zoom from 9 to 10. Well, that's how every student is going. So, calculus is different than project. You do run this one. If you go into the math, if you're big right now, we have a math lab on this campus and my side campus. It's in the A building upstairs in the library, it's in the left. And they as well. I actually have class right now, I just like yet. But you check there, I'm also going to be in the John Muir building 2 to 3 on Friday. And then, are you free on Saturday? Okay, yeah, like I teach in the evenings and afternoons, so like usually the weekend ones kind of really have a lot of free time. Try the non-pop stuff. They all know how to do it. No problemo.